wanted to verify that you can hear my voice.
Yes.
Thank you for confirming. Okay, we have first, welcome back to the second session of the OpenMBE workshop at Models 2020. We had a great morning here with the introduction and keynote from Ed, followed by 2 papers and good discussion around those topics. For the second part, we're going to jump right into the first keynote, followed by two papers. Keep in mind that there are Q&A times with each one. The deadline, a minute or two on either side isn't a big deal, so I won't be interrupting you. But do ask questions. We want to keep this conversational here. So for the sake of time, as you can see, we have a pretty packed schedule here. We'll jump right into the first keynote given to us by Marcus. We're very excited to have him share his expertise, vision, and ongoing work with language workbenches, and share with us a vision for systems engineering on the web. Without further ado, Marcus, I hand it over to you.
All right. Thank you for the invitation. I'm going to share my screen, and you could please confirm that it will work, hopefully. You should now see my PowerPoint presentation mode.
Yes, Marcus, okay, we do. Full screen.
All right. Okay, good. Yes. So, well, I have spent the last 10 years building languages in all kinds of domains, from business over healthcare to engineering, embedded safety critical systems. And I did that mostly based on JetBrains MPS, which is great, but of course it's not the future. It needs to be, everything needs to go into the web and into the cloud. And so for a while I've been thinking about how I would see a future web-based collaborative modeling environment for large-scale models, multi-paradigm models, which is basically the definition of systems engineering. From a modeling perspective. And so I want to share some ideas with you. I'll resolve at the end where I think the connection to these huge cranes comes from. Maybe you can guess. So let's start with some of the requirements for such a tool. Obviously, it needs to be scalable. As you know, probably better than me, or certainly better than me, systems engineering's models are often quite large because the systems are large, and the models will become larger over time because we want to probably model more aspects of the system. So scalability in terms of model size and numbers of users and organizations is crucial. Then the whole thing should be web native, which means that it should use, the paradigms of the web, good usability, URLs should be able to be used meaningfully to address model elements. Things like REST APIs are important. It shouldn't be a desktop tool, somehow faked into the web. It needs to be collaborative, and we've kind of all agreed on Git as the lowest common denominator for collaboration, but in my experience, many people, while they somehow are able to accept Git after a bit of pressure or whatever, many people want something that's more like Google Docs, a real-time collaborative environment where people can jointly work on models and, evolve them, analyze them. And so I think, at least optionally, such a real-time collaborative environment should be available, plus, of course, an ability to work with files, Git style. No, somehow the focus was lost. I think we should, as a modeling community in general, we should emphasize more what the programming community calls live programming, where the separation between designing a model and running the model should be less strict. Now, in systems engineering, we don't necessarily model executable programs, but the models can still be executed. Execution might be an analysis. Execution might also be actual execution if we, for example, model a state-based system. And having the ability to interact with the execution of a model is really important, especially to get non-programmer type stakeholders on board who might not be that good at, just looking at an abstract model and understanding what this means. Then, of course, versioning and migration is important. And by that, I mean not versioning of the models, although that's obvious that we need that too. I mean versioning and migration of models as we change the languages we use to describe these models. Because in my experience, if you want high fidelity models, you need custom languages, domain-specific languages mixed with general purpose languages. I'm not trying to argue against things like SysML, but you should be able to mix standardized languages for those things where a standard makes sense and domain-specific languages for stuff where there is either no standard or maybe it doesn't make sense. And then, of course, these languages evolve as your understanding of the domain evolves. And so you have to do something with your models. And many modeling tools don't do this very well. And so I think this should be designed in such a system right from the start. And then, of course, roles and viewpoints. As we have diverse stakeholders, we need to be able to define, different languages for different roles, different views on the same model, depending on what task you do and stuff like that. Again, something that in many of today's modeling tools is only is supported to some degree, but not really well. Related to that permissions, I want my colleagues to be able to look at the code or the model, but my supplier should only see the interface definitions, but not the implementation. So of course, if we work with files, we can just send the respective interface definition files, but in a repository-based approach, which is probably necessary to do the collaboration in real time, we need to build something specific to support this. And then finally, something that is also often forgotten and about which I've heard some fun stories very recently from the German automotive community, negative stories, unfortunately. All of this needs to be integrated with a continuous integration. So you have to be able to pipe those models into basically a built infrastructure which generates code, generates other models, runs analysis, generates reports, documents, stuff like that, and runs tests. And so this needs to be a design concern right from the start. So these were all non-functional requirements. They all are quality attributes mostly of a system like that. I didn't say anything about the kinds of languages. And so let's look at the functional language, requirements. I think in terms of user-facing functional requirements, I think it's really important that the environment is multi-notation. Ed mentioned something about this morning in his keynote, where he pointed out that SysML v2 is by default textual, or not necessarily by default, but everything is available as a textual language. But then there will be tabular notations, diagrams, of course, and even maybe very strange other notations that are really domain specific. We've worked on projects where the notation was inspired by the domain, but you couldn't easily pinpoint and say, well, it's a table or it's a diagram. It's a mix of stuff. And then we want, again, as I said before, multi-paradigm, mixing standardized languages with domain-specific ones, maybe even adding domain-specific extensions to a standardized language. And then we want really great IDE support. I think it is fair to say that if we compare modeling tools and their user experience with coding tools, classical IDEs, IntelliJ, use those as a comparison, then I think the programming tools probably win in terms of usability, scalability, productivity. And I want something like that for my modeling languages as well. Now, if we have domain-specific languages, then another target audience for such a tool is, of course, the language developer, right? They should be able to easily and productively add new languages. So we need meta languages for language definition, and we need language modularity, as I pointed out before. So we can take an existing language, for example, SysML v2, and add domain-specific extensions or integrate it with other domain-specific languages or other languages on the same platform that are not necessarily in the scope of SysML. And just for reference, I just want to briefly point out what MPS can do in this context, just as a reference. I'm not trying to sell MPS. Actually, I don't think MPS has a big future in the web, even though I'll show a prototype of exactly that later. I think we need something different. But in terms of the available feature set, I think it's a good reference. So MPS is a language workbench, and as the title of my keynote suggests, I think that language workbenches are the environments that should be the underlying platforms for productive modeling tools. Language workbench means it's a tool for defining your own languages, and language definition here includes defining structures, meaning abstract syntax tree or meta model, notations, a wide variety of notational styles, type systems, constraints, transformations, generators, refactoring, syntax coloring, debugging, execution, tracing. All of these kinds of things are supported by existing language workbenches to one degree or another. There's a whole set of language workbenches, most of them open source. There's a paper from 2013 that compares them, a bit outdated, but most of the current ones have still been available back then. Anyway, and I think MPS is one of the more powerful ones. One reason is that it does support language modularity quite well. Basically, it allows you to do product line engineering on language level, right? You can take independently developed languages and merge them in the same program and have one extend another one. It's a very powerful environment because you don't have to redevelop your languages from scratch all the time. There are obvious candidates for reuse, things like expression languages, namespaces, then of course, languages for defining structure like SysML, state machines. You don't want to redevelop them just because you need some kind of extension. So you want to take the existing one and modularly add stuff you need, or also constrain things out that you don't need. And then again, this notational freedom, the ability to have a wide variety of notations, mathematical notations, tables, diagrams, is really important to get buy-in from a wide range of stakeholders. And we've done this in business systems where we talk, for example, to financial analysts and build languages for them, but also for a wide variety of engineers who are maybe a little bit more amenable to structured and formal models than maybe financial or government analysts are. But just doing everything textually with the typical Eclipse keyboard colored and a whole bunch of curly braces, it's a hard sell. So the more flexibility you have regarding the notation, the better it is. So here are just a few examples. I'm not even going to talk about them much. These are all languages defined with MPS. Here is one that is a mix between something like a form and a language. Here is a very weird notation for temporal rules that you can see our customer originally prototyped them in Excel, because of course this has been an Excel table at some point before we put it into MPS and made it kind of strongly typed. You can also see these things here. These are basically expressions written in C with a bunch of C extensions. So we have C plus extensions embedded in a proprietary language, but all syntactically integrated. Then of course you have the usual diagram connector port thing, C with a bunch of math stuff, tables for making complex decisions, decision trees, decision tables, and something that is basically just looks nice. It's a language for defining how to weave safety patterns into C code. Again, I don't. It's not important how you do this with MPS or any of that. Just my point is to widen the understanding or the impression of what syntax can be, because again, it's very helpful to be able to convince prospective users. So the proposed infrastructure for such a tool, in my opinion, should look like this, and I'm going to explain. So I want a distributed storage of the models, and I want them to be stored as graphs or trees, but not as blobs, not as files which have to be reparsed whenever you want to do something with them. So the storage should know about the granularity of nodes. I want incremental transformations. So if I push something to the storage, depending on the kind of change, a transformation is triggered that updates other models, for example, type checks or a simulation or a model check. I want an open API for transformation-based services so I can plug in additional services. Some external tools, again, for example, a model checker. Probably we don't want to redevelop this to plug into this incremental transformation framework, so we want to be able to kind of integrate batch-oriented tools as well. The server nodes should be replicatable or replicable for scaling out. We want an open API for Delta-oriented front ends, by which I mean every change you make to the model, every node addition, every property change should be communicated to the server as a Delta, triggering the respective transitions as transformations. For multiple users, we want conflict resolution based on operational transform or CRDTs. Basically, this gives you the Google Docs style real-time collaboration with immediate conflict resolution. We want REST-style APIs for bulk-oriented clients, like exporting complete models for some kind of client-side analysis. And of course, there should be a layer that does authentication authorization. There's a white paper I wrote a while ago that captures some of these ideas. There's a QR code and a URL if you want to read more about this. So obviously, the idea is kind of simple to have. I want to say something about a prototype we've been building. It's called Modelix. It's developed as open source software by a bunch of folks at Itemis and a few other people starting to join. Right now, it is based on MPS, and I'll say something about that and how we're going to get rid of this. So it has a model repository. It stores models on node level as a node graph, as I said. It has a Gradle plugin for CI integration, and it supports a Git-like history and real-time collaboration based on this kind of database-y model repository. It automatically supports all existing MPS languages, again, because it's MPS-based for now. It has two kinds of editors. One is image-based, where it basically projects MPS's editors into the browser, and that's why every notation already works out of the box. But there is another editor that is going to be more important in the future, where you define your language, the notation for your language basically as an incremental transformation on top of the browser DOM, right? Then we have a bit of GitHub integration to show diffs, and there is a whole Kubernetes infrastructure to deploy all the backend stuff onto the cloud. Basically, it looks like this. If you have your browser here, there is a little bit of JavaScript that's called the UI client that talks to a bit of a web server running in an MPS in the cloud. And so whenever you make a change to the model, this change is propagated here, and then the existing MPS type checks and other language services execute, and you get the updated error view or red squigglies or model changes. The infrastructure on the server, Docker-based, runs a whole bunch of MPSs, which is also nice because sometimes MPS tends to become unstable and die a little bit. And so here we have just a watchdog that kills it and starts another one. Because the models are all stored in the database, it doesn't matter if we kill an MPS and fail over to another one. Of course, you can interoperate with client-side MPSs as well. It would then just directly talk to this database. So yeah, I just said what these bubbles say as well. Now here is where it becomes interesting. This model server right now, this is just a dumb database. It doesn't do anything except storing on the level of nodes. But the plan is to get closer to this vision I pointed out before, to add more and more services that work directly on top of this model representation in this database. So right now, for example, the type checker runs in MPS as an MPS language on the MPS representation. We'll develop a type checker and a way to specify type systems on this level, so we can step by step get rid of MPS here, and at some point we just don't need this anymore and everything runs on this database with these services, again getting closer to the vision I've pointed out before. Now, to close my talk here, a few more relationships to systems engineering, because I mean, this infrastructure I'm proposing here is of course generic. I think it is particularly useful for systems engineering because of this large size of models and multiple languages and large number of stakeholders. But of course, you can use it in any other domain just as well. Here is something that is specific to systems engineering. We have prototyped SysML v2 in MPS and by implication also in ModelX. And we focused on implementing the basics of SysML v2, but then integrating it with existing languages we've already had available to point out why and how language modularity is useful here. So here is basically a SysML2 package, and then we have a bunch of values here, and these are typed and given a value with expressions written in a language called kernel F. That is a functional programming language we use in MPS as the basis for all kinds of DSLs. And as you can see here, we can call functions, we can use mathematical syntax, we can use decision tables, and it kind of works out of the box. So we've composed the SysML language with the kernel F language without modifying either of them. Here's another example. We have a existing product line variability feature modeling language in MPS with a solver-based configuration engine. And we can now annotate SysML models with those variant expressions. And then as you change the configuration here, you can see live how your SysML instance model is basically customized based on these presence conditions from 150% model. We have support for physical units, and we have also implemented this language extension example for the glucose meter, where we basically have custom syntax, relatively boring custom syntax, but custom syntax nonetheless, for basically defining one of these fault trees, I think it's called. I'm not sure exactly which fault analysis methodology it is, I forget. But anyway, we incrementally transform this to pure SysML, basically to instances of SysML concepts or model elements defined as part of a library, which is kind of this mapping from custom syntax to an instance of a generic library. So I think an infrastructure like this is necessary to be able to do the heavy lifting for large systems engineering projects. And this heavy lifting is also kind of where this connection to these cranes comes from. I did spend quite some time this summer taking pictures of large cranes, and I thought this would be a good kind of fit here, because I really do think that if we are really able to put, you know, a 747 or whatever is, you know, 777X into a systems engineering tool, we need something that can scale really big. And although I'm not claiming I'm able to implement all of this, I'm certainly not. I think the vision is something to ponder. And so I'd love to get your feedback and ideally your involvement to build something like that together in the context of OpenMBE. And obviously there are also some parts already there. All right, I'm done. Questions? Did people fall asleep?
No. Great presentation, Marcus. Thank you very much. I'm reviewing the chat here. Feel free to drop questions in the chat box, or if no one else is speaking at the time, you can unmute and ask your question verbally as well. Daniel says hi. So I assume, oh, there we go. It's flooding with questions now. Daniel, you can go ahead and ask your question out loud if you want, and in 5 seconds, if you don't, I'll ask it for you.
Hi, Marcus. How are you dealing with element IDs? Because you showed a textual representation of your model, and how do you do the mapping behind the scenes so the elements keep the same IDs during the life cycle?
We do not at all, because MPS is not parser based. It's based on a projectional editor where every node has ID anyway. So there is no architectural difference between a textual notation and a graphical or tabular one, which is one of the benefits. So there is no mapping back and forth. So yeah, it's not a problem.
Marcus, I was wondering, I'm not sure if the microphone works.
It does.
what is the biggest roadblock right now when it comes to heavy lifting? If I had to, pick up the challenge that is going to give the biggest return right now,
Yeah.
To get 777x into the modeling environment, which is the biggest roadblock?
Yeah, of course, obviously different people have different opinions there, right? I think that so if you want to have real-time feedback on whatever it is you model, either things like static analysis or live programming style executing models, you need a very reactive transformation engine that, practically speaking, probably incrementally runs the transformations as you change the model. And so I think a scalable, incremental infrastructure for storage and transformation is something we really, as a backend of something like this, we really don't have that. There are, of course, ingredients in query, right? And there are databases that are able to store huge amounts of basically, graphs by storing them as just, name value pairs and stuff like that. All the ingredients are there. But tying all of this together into a robust infrastructure that scales well and stuff, is not available.
So it sounds much harder to build in Google Docs. To me,
I'm not actually sure it's harder than Google Docs, because you have a well-defined schema in the backend. It's much easier to, or it's not. I mean, the collaboration part we have running, right? That works. We do have that in our prototype. So so what makes Google Docs interesting, is the collaboration. We have that solved. That works. And what we don't have is the incremental transformation. I mean, we have prototypes, of course, but nothing that scales really well. And that is not very much related to what Google is doing. It's just a different kind of problem, I think.
Thank you.
Great. I think there are a couple more questions in the chat. Feel free to unmute and ask them.
Yes, so there's a comment from Ed, right? Whether what I'm proposing requires the clients to use projectional editing. And so my answer to that would be, basically, I would, if you think back about my slides, I said there are different kinds of editors in the front end. I called them delta oriented. Now it is of course up to the editor to decide how big the delta is. And so if you want to build an editor that is parser based in order to avoid the need for projectional editing, and you, for example, do you implement some mechanism to retain stable IDs and have a differential parser to come up with the deltas, which there are techniques that do that, not a big deal, then I think it's totally feasible to connect a parser-based front end to that same infrastructure. Maybe the deltas aren't quite as fine-grained as in a projectional editor, where every property change and every node creation deletion is by definition a delta automatically. But okay, then maybe the UX is a little bit less fine-grained, but you have the benefit of a textual editor. So I think that's a perfectly fine trade-off. So we had at Itemis, we had a project a while ago where we tried to do something similar. We gave up because it was too much work for us as a small company. And we started with the client side and we said, everybody has to do projectional editing because it's so cool. We gave up on this. We are now much more focused on the back end, on the transformation infrastructure, on the incrementality, on the repository, and then we can plug in different front ends with different trade-offs regarding incrementality and potentially user experience for the editor.
Okay,
great.
thank you.
I'll go ahead and ask Benoit's question. Thanks, Marcus, for the great talk as usual. Just wondering if you have any idea of the structure of the graph to store on the repository. Do you plan to bind the structure to a particular meta language or technological space, or being agnostic to any meta language?
So it's of course specific to it's a layered system, right? So right now we basically just store a property graph, which is you can't get very much more generic. So the interpretation of the models relative to a meta model and even the meta model is currently done in the client. So the database is completely dumb. I think it's probably useful, and we are building a prototype for that layer as well right now, to basically also have an API to that low-level storage that knows about the meta language, EMOF, something like that, right? And then having a way of course, interpreting a generic, graph in terms of a particular meta model. So I think in that sense, it's the usual layered approach that is used in tools like MPS and Eclipse as well. I hope this answers your question, Benoit.
Yeah, thank you so much, Marcus. I was just wondering, I was much on the meta language, so the meta model. I was just wondering how we can bridge at some point the gap in between XTeX, NPS, Rascal, and whatever, because they are all very good advantages. And right now, when we are choosing a meta language, which is most of the time linked to a language workbench, it also binds all the choice in terms of how the model will be stored, will be structured, and then how they will be manipulated.
I mean, I think most of the meta languages of all the languages workbenches are basically kind of the same, right? There's not much difference except maybe in meta case. So I think agreeing on something that is common, I think, is not too much of a big deal. Also, if you then over time want to move more of the services into the backend that work on that kind of service as a repository layer with these services, well, then by definition, you have one infrastructure and not 25 different ones.
Yeah, I agree with you, but it's exactly the point. Is it possible to provide a common interface, such as tomorrow I will be able to use Rascal for manipulating EMF models, for example?
I think it is possible. I mean, as long as the abstractions for defining languages in terms of their structure are reasonably similar, basically EMOF, which they all are, I don't see a big problem. I mean, right now we basically export the database level models into an EMF model, into an MPS model natively to work on it in the client. There's absolutely no problem to do the same for EMF. Well, I mean, whether this is realistic, whether we're going to build all these tools anytime soon, and that's a different question. But conceptually, I don't think it's a problem. We've built interop between MPS and XTeX, for example.
Yep. Thank you.
Fantastic. And just a note that we can always follow up further in the chat or some of the other communication channels that we'll be talking about in the outro. But feel free to keep the conversation going there. But with that, thank you very much for that great presentation, Marcus. Want to switch it over to Andres now to present his and his colleagues' paper on Breeze. Whenever you're ready, Andres, you can share your screen.
I just shared my screen. Can you confirm that you're seeing it?
Yes, we can.
Okay. So hello, everyone. In the last session of this workshop, we were hearing about a lot of about consistency. So this work is rooted on consistency. So it's about bridging EMF, Simulink, and stateful for model-based design of safety-critical systems. So to tell you about how we started with this work, so we're working with 2 aerospace companies here in Montreal to help them with their airworthiness certification efforts. Now, these 2 companies design avionics systems using a mix of UML, Simulink, and stateful models. So when they were preparing for an airworthiness certification, they had to deal with all this information that is spread across multiple models that are expressed, each one in different modeling languages. So what we saw was that there were many inconsistencies creeping into these models. Now, as part of their certification processes, they have to ensure consistency between all these heterogeneous models, and they have to do this manually. So this is both resource consuming for them and error prone. Now, existing verification validation tools do help them, but these tools, they output results that are isolated to one design model. So the result is not enough to provide the required level of safety assurance that is needed for an aviation system. So we proposed an approach that comprises a methodology and a tool framework that will automatically flag inconsistency errors in the various design models. Now, this work has been published in IEEE Transactions on Software Engineering. There's you can see the link there. Now, this methodology can be applied to various design scenarios involving different modeling languages, not just UML, Simulink, and Stateful. But part of the methodology entails deriving a tool support element. So we instantiated the approach for the design scenario of these two companies. So that is a mixed use of UML, Simulink, and Stateful. And we derived an Eclipse toolchain. Now, this as part of this toolchain, we incorporated what we call Breeze, and that is the work that I'll be presenting in the next slides. Now, this the Breeze enables the model consistency analysis by bridging the Eclipse modeling framework and the MathWorks Simulink and Stateflow ecosystems. Now, a number of tools have been developed to support this kind of integration. So we have Matclips that provides an interface between Eclipse and MATLAB to enable the usage of MATLAB directly from the Eclipse IDE. Now, with Matclips, the tool does not offer interface support for Simulink or Stateflow, which limits its reuse for MD. We also saw the LiOSLC Simulink adapter that provides services for handling Simulink elements outside the MATLAB environment. Now, LiO's main advantage is its open communication interface, allowing an application, not just Eclipse, to interact with Simulink. Unfortunately, the tool does not offer support for Stateful, so we couldn't use it. We also have Massive, which is a live bridge between Simulink and Eclipse for enabling MDE workflows. Massive connects directly to a running MATLAB instance for importing and exporting Simulink design models into and from the Eclipse IDE. It is very flexible. It can handle different model import-export scenarios. We did have a problem when we try to use it in our context, is that it uses Viatra model queries to populate some of the derived attributes in the resulting EMF models. Now, we experienced some issues when we were trying to use those resulting EMF models in other EMF-based Eclipse tools. So those Viatra queries were not executed, so we couldn't retrieve all the information that was necessary. And last, there's an on-the-fly translation approach that eliminates the need for an upfront transformation of Simulink and Stateflow models. Now, this has some performance gains over approaches with an upfront transformation like Massive. Although in extensive querying use cases, that performance is lost. And actually, Massive would be much better in those scenarios. So we based ourselves on Massive and we created Breeze to solve some of the issues that we found with Massive. So Breeze is also a live generic bridge for EMF Simulink and Stateflow. It is realized in Java with EMF technologies. It uses the MATLAB Engine API for Java to directly connect to a running MATLAB instance. It is able to import the contents of Simulink and Stateflow models into an EMF-based representation. This EMF-based representation enables the manipulation of the imported models with other EMF-based tools for MDE. So a user only has to right-click over a desired Simulink model file, like we see in the picture there, and select a context menu option. And then it processes the model. And once it's done, Breeze will output the resulting EMF-based model into the same directory as the original model. Now, three components make up the core of Breeze. So we have the first one is the EMF-based Simulink and Stateflow meta model, to which all imported design models conform. The second component is the Simulink and Stateflow importer component, providing facilities to import the contents of Simulink and Stateflow design models and to create an EMF-based model conforming to the EMF-based Simulink and Stateflow meta model. And the third component is the command evaluator component. This component allows us to create the generic bridge able to support the wide range of operations. And it integrates the MATLAB engine commands as object-oriented constructs that are then translated and sent for execution using the MATLAB engine API for Java. Now, we built our meta model iteratively after a careful analysis of the Simulink and Stateflow documentation. Now, here's a simplified fragment of it. For Simulink, it is primarily an adaptation of Massive's EMF Simulink meta model. Now, for Stateflow, because of Massive doesn't support Stateflow, we introduced new concepts and relationships in order to do that. Now, the MATLAB engine API for Java enables the interaction with MATLAB from Java programs. However, it is based entirely on the expression of commands as simple strings without any validation done at compile time or even content assist support. Now with Breeze's command evaluator component, we wanted to provide a framework for integrating the MATLAB command evaluation capabilities as object-oriented constructs. Now these commands are now written against a strongly typed command object using Java's familiar syntax. And this helps guarantee their correct construction. It is worth mentioning that this command evaluator framework is reusable on its own in other application contexts that may involve interaction with the MATLAB from a Java program. There are some limitations though with that we inherit from the MATLAB engine API. The MATLAB engine API has a limit on the length of the outputs that are returned from command evaluations. So certain elements in the resulting EMF-based representation may end up with some truncated data. Now, this is an issue, especially in the context of safety critical systems. Now, this can be handled directly into design standards that could be redefined in order to account for the issue, but that is not a viable solution in all cases. Now, we plan to devise some mechanism that will mitigate this risk of having truncated data in the resulting models. The Simulink and Stateflow importer component delivers the model importing and saving capabilities. Once the user selects the desired Simulink and Stateflow design model to import, Breeze's importer component proceeds to build the EMF-based representation. And this build occurs in three phases. So the first phase handles all Stateflow constructs Every state flow chart is analyzed and processed in 3 steps. So it defines the EMF-based representation for all its contained elements, regardless of their hierarchical structure. Then it sets the properties of each contained element. The third step is to establish the correct hierarchical structure. Now, every one of these steps originates a set of high-level operations for extracting information, which are built on top of the facilities that we provide with the command evaluator framework. The build process continues with the build of Simulink blocks. The second phase handles all remaining blocks in the model that are not state flow charts. And like in the previous phase, every block is analyzed and processed following the same 3 steps. Then finally, the process ends with the interconnection of all blocks. And now this third phase analyzes the origin destination of all the connections in the model, and then generates their corresponding representation and links the corresponding EMF-based blocks. The output of this phase is the expected EMF-based representation for the given Simulink and stateful design model. We used Breeze on 3 avionics systems, a landing gear system and a flight control system and an elevator control system. Our industry partners, of course, were involved in this. They consider the systems as representative of their own products. Here we show some fragments of the design models from these 3 systems. And we process them with Breeze. Now this table summarizes the model contents in terms of the number of elements, of element types they have. And the last row presents the processing times for Breeze to generate the EMF-based representation. Now, building these representations is a bit of a computationally demanding activity that depends on the model size. Now, scalability is an issue for upfront transformation. And our reported processing times are rather slow for models that are relatively small. Now, this is due entirely to MATLAB because it has to evaluate the commands that are given to it one by one. Now, depending on the amount and type of elements, these evaluations may take longer for some commands. So Breeze cannot obtain a result for a command until MATLAB has output a value for that command. So from our experiments, design models with larger stateflow structures like the LGS and the ECS, design models took longer time to process than those with fewer stateflow structures, but larger Simulink structures like the FCS. And now, despite the high processing times, this is a one-time effort that can be offset when models need to be extensively queried, which was the case with our industry partners. A mechanism for fetching information on demand could be included to improve the performance by not building the entire presentation at once, but doing it incrementally as it is needed. Now, these are the images that you're seeing right now are portions of the resulting EMF representations. We recruited engineers from academia and industry to help verify the consistency between the original Simulink and stateful design models and their resulting EMF-based representations. All these engineers had a strong knowledge on MDE, and they all have experience with Simulink, stateful, and EMF. They reviewed the models according to criteria. So they checked for the elements in the resulting model and traced them back to the source Simulink and stateful design model. And then for the Simulink part, they checked that the blocks in the resulting model were connected as they appeared in the source Simulink design model. And the same thing for the stateful part. Now, the engineers found that all design models were correctly imported. We do note that we do need a more robust and thorough validation of consistency. This could be achieved through the use of formal methods. Now, to conclude, safety critical system development can be improved by leveraging model-based design and verification tools in the form of an integrated environment. We presented Breeze, a live bridge for the Eclipse modeling framework and the MathWorks Simulink and Stateflow ecosystem. It is available to the MDE community as an open source tool. And we created it as part of an applied research project with 2 aerospace companies that design avionics systems using a mix of UML, Simulink, and Stateflow models. These 2 companies needed to ensure consistency between these models. So therefore, we proposed an approach to address this issue, and Breeze serves as the enabler technology for that. Ongoing research and development aims to formally verify Breeze's outputs, improve the functionality and overall performance of the tool, and of course, add new features. That is it for me. Thank you very much for your attention. If you have any questions, feel free to ask.
Thanks, Andres. As usual, chat if you have any questions there, or feel free to ask. I'll start off with one more a clarification from the Eclipse user interface or the IDE. Just clarifying that the intention is to be able to execute through the MATLAB API the actual Simulink model. Is that correct?
Yeah. So if I go back and oops. Sorry. So if I go back to here. So when you have your Simulink model inside a project in Eclipse, and then you want to import it. So when you select the option to import the model, it opens up MATLAB. It opens up the Simulink model in MATLAB, in a MATLAB instance. And then it starts to send commands into MATLAB to retrieve all the information and then build the EMF-based representation. And that's what we get on the right side of the figure there.
Gotcha. Thank you. And just a follow-on question there from me, and then we'll let someone else go. You mentioned that one of the future areas of work would be some sort of like formal methods or some sort of analysis on the imported model. Can you think, or can you share maybe 1 or 2 types of analyses on the imported model that might be interesting to the groups you're working with?
So what I was talking there was more on the verification of the consistency about between the original Simulink model and the result that we get from the tool. But the kind of analysis that we've done with these imported models is consistency between the part. So we have a system that's modeled with different modeling languages. So we have Simulink, Stateflow, UML, and all these models, they contain different parts of the system. But when you build those models, you tend to introduce inconsistencies because not just one person is involved in the creation. So what we do with this, the analysis that we do is try to ensure consistency between all these heterogeneous models. And that's the reason why we needed Breeze to bring Simulink models and be able to process that information alongside UML models.
Oh, okay, gotcha. So Teresa had a question. Feel free to ask it if you want, or I can relay it.
So
Well, I can jump in.
you can ask it if you, yeah.
Okay, great.
Yeah, go ahead.
So yeah, I was when I looked at this breakdown of the model structure, it struck me that all the components, like especially subsystems, are all the same type of component, right? Like we don't have things like model reference or function calls or variant subsystems going on. Was that because you could, everything looks like a subsystem to your system, or is it that no, it just happened to be the way these models were configured?
Yeah, it's sort of both things at the same time. Yeah. So when we built these models, everything to us looked like a subsystem, and then inside of those subsystems, we have a chart or several charts that describe the logic that each subsystem has. So inside of every subsystem there, you'll find several charts.
I see. And then on the
Yeah.
ports, are you picking up bus structure on those too? I couldn't quite tell here if it's the case that the structure of the bus going into the port is also being picked up, or is that is it just looking like a signal to you?
No, it just looks like a signal for now. It just looks like a signal. So we get a signal from the inputs and then output another signal out.
Okay, cool. And then the last one was about System Composer, which is relatively new. So I wasn't sure if you had considered that for this, or like what information you could have pulled from System Composer that would have helped you with interpret. I don't know if you looked at it at all. I guess that's my question.
No, we didn't look at System Composer.
Okay, thank you. Those were my questions.
So yeah. Oh, thank you very much.
Great. Thanks, Andres, for presenting that for us. We'll switch to the next paper presentation. Last but not least, Benedict will be sharing with us model checking as a service.
So, welcome everyone. My name is, can you see my screen first of all, the presentation?
Yes, we can.
Okay, thank you. So, welcome everyone. My name is Benedict Horvat, and today I would like to present you our paper, Model Checking as a Service Towards Pragmatic Hidden Formal Methods. In model-based systems engineering, models are cornerstones of the whole engineering lifecycle, starting from requirements through design, implementation, and finally documentation. There are several commercial tools available for designing and simulating systems engineering models. In recent years, there has been a new trend which moves the focus from the client machines to the cloud, where more computational resources are available. Part of this trend is the emergence of open collaborative modeling environments like OPENMBE. OPENMBE consists of several components which enable the collaborative work of engineering teams. One of the components is the model repository, MMS. Inquiry Server is a design analysis and review tool for checking and validating engineering models. It has a scalable query evaluation engine to analyze engineering models in MMS to find structural errors in them. The correctness of the behavioral models is a cornerstone of the engineering processes in MBSE. There are several simulation and testing techniques available which can check the correctness of the models. However, they might not be able to find every error residing in them. Formal verification relies on mathematically precise formalisms and algorithms which can explore all possible execution traces, not just a selected few. Besides, if the model is erroneous, then these techniques are able to return an example trace demonstrating how the erroneous behavior can occur, which can help the engineers to find and fix the errors in the models. Although formal verification can systematically traverse the model, it has several challenges. First of all, these techniques have high computational resource demands. If multiple engineers are using the same validation and verification workflows so that they are running parallel verification tasks of multiple users, then these verification requests should be quickly served by the workflow and by the system. And third, there is usually a semantic gap between the engineering and formal domains. It means that the formal verification methods should use the same executional semantics so that the example trace that are found by the model checkers can be also replayed and validated in the engineering domain, thus demonstrating how this erroneous behavior can occur and the engineers are able to find and fix the problems. In order to tackle these challenges, we set several objectives. First of all, by leveraging the elastically scalable computational resources of the cloud, the scalability issues and challenges of model checkers can be tackled. For example, dynamically more and more memory and CPU can be allocated to the model checkers so that they can perform the verification. In order to serve multiple verification requests of engineers, more model checker instances can be started in parallel, each of them serving one of the tasks, one of the verification requests. And in order to bridge the semantic gap between the engineering and the formal domains, semantic preserving transformation should be used on the one hand, which enable that the example trace that is returned by the model checking can be examined in the engineering domain. And on the other hand, we should start with a restricted but meaningful subset of the engineering language, which means that although there are several standards which define executional semantics for engineering languages, sometimes these standards are ambiguous or not complete. However, they usually have a subset of elements for which the executional semantics is clearly defined, so that the work should be started with this initial subset, and then this set can be gradually extended with new elements by defining semantics to them and by providing feedback to the standardizational bodies so that the standards can be extended as well. In order to prove the applicability of the objectives, we created a proof of concept implementation of a cloud-based verification workflow for SysML state machines. SysML is the standard modeling language in systems engineering. We started with an initial subset of modeling elements in state machines for which the executional semantics are clearly defined. In this figure, you can see a state machine of a simplified spacecraft. The figure depicts all the elements that are supported by the workflow. The main state of the state machine has two regions. One of the regions is responsible for modeling the data transfer. The other one is responsible for modeling the battery control. The battery might be in not recharging or recharging states. In the data transmission, first the state machine is waiting for a ping signal to arrive. As soon as the signal arrives, the state machine starts sending and receiving data packets from the ground station. Meanwhile, the data transmission consumes battery so that the battery will be depleted in the end. Although this state machine is rather simple, we would like to verify that several properties are satisfied by the model. For example, we would like to check that the state machine should never transmit when the battery is below 40. Although the battery below 40 condition is on both outgoing transitions of the transmitting state, traversing and exploring all possible behaviors and all possible execution paths of this state machine can be cumbersome if we have to do it manually. So that we need automated methods which can automatically traverse all possible execution traces and prove that there is no such configuration when the state machine is in the transmitting state while the battery is below 40. In order to prove that such erroneous configurations do not exist, we define reachability properties. Reachability properties define state predicates of a faulty behavior, and the goal is to find a trace where the predicate is true, thus demonstrating that this erroneous behavior can occur. In order to represent reachability properties, we chose the sequence diagram formalism. First of all, because the systems engineers are already familiar with this formalism, and second, because they can intuitively represent reachability properties. Reachability properties can consist of states of the state machine, and can have conditions over the variable of the state machine. And the goal is to find a demonstrating trace that shows how the state machine gets into the erroneous state configuration, starting from the initial state configuration. And using this trace, the systems engineer can replay it and find where the behavior deviates from the originally planned behavior, and they can figure out how to fix the models. In our work, we reuse the gamma state chart composition framework. That is a framework for defining the behavior of systems. It uses the gamma state chart language to model the behavior of the systems, and it has several formal compositional semantics to build composite systems. And one of the big advantages of the gamma state chart composition framework is that it can transform the state charts into the input formalisms of model checkers. It can invoke the model checkers and verify several formal properties of the models, and the verification results are also automatically back annotated to the gamma language, so that the results can be proved, and it can be seen how the model gets into this faulty behavior. And in our work, we adapted this gamma state chart language. First of all, we transform SysML state machines for the gamma state chart language. And the other aspect was that to enable the cloud resources, we enabled the gamma, we adapted the gamma framework for cloud execution. Now let me introduce the validation and verification workflow. So to prove the applicability, we defined the workflow and implemented a proof of concept version of it. At the beginning of the workflow, systems engineers are designing the state machines in their SysML tools. They are uploading several revisions of the models into the model repository. Besides the state machines, they also define reachability properties that they want to verify. In the second phase, they open a web browser to start validation and verification actions. They select the state machine that they want to verify. They also select the corresponding property, the corresponding reachability property for which they want to evaluate the state machine. And then they start this validation and verification, which will be detailed in the following slides. Now I would like to quickly highlight how this workflow is satisfying the objectives that we set previously. In order to enable leveraging the cloud resources, the main components of this workflow are containerized and can be easily deployed to the cloud. In order to meet the semantic integrity goal, we started with an initial subset of modeling elements in state machines, for which the PSSM standard clearly defines the executional semantics. And we chose an intermediate language whose executional semantics is similar to PSSM. And the other advantage of the intermediate language was that the new model checkers can be easily integrated, because we just need to transform the SysML model for this intermediate language, and then the intermediate language will take care of transforming the models to the input formalisms of each model checkers. So after the users chose the state machines and the reachability properties they want to verify, the MCAS model checking as a service add-on of inquiry server is performing static checks on the models. It is checking that the state machines only contains the allowed subset of modeling elements for which the executional semantics are defined. And these webformness constraints were implemented using the VRTRA query language. After that, the add-on is transforming the SysML state machines for gamma state chart language, the reachability properties for gamma property language models. And during the transformation, we are building a traceability model that is used later in the back annotation phase to get back the validation results from the gamma language and to be able to back annotate it into the SysML language that can be returned to the engineers. So after the transformation, the gamma framework is responsible for translating the state charts into the input formalisms of the model checkers and invoking the model checkers as well. In our workflow, we use UPAL as the model checker. UPAL is using timed automata as formal models, and then the reachability properties are translated for liveness queries in CTL. After that, the gamma framework is invoking the model checkers, evaluating the formal properties on the formal models. And in case the reachability property is satisfied, which means there is an erroneous state configuration which should be returned, then this demonstrating trace is returned to the is returned by the model checker. The gamma framework is responsible for translating this trace to the gamma trace. And after that, in the 7th step, the MCAS add-on is responsible for translating the intermediate gamma trace into system sequence diagram and return it to the user so that they can inspect how their systems goes wrong. And to conclude our work, we defined a scalable cloud-based workflow to verify SysML models using hidden formal methods. We identified an initial subset of elements for verification. And thanks to the semantic integrity of the workflow, the example trace is simulatable in the systems engineering tools. And as for the future work, we are planning to add new model checkers to the framework, for example, Zeta. We are planning to experiment with the adaptive scalability and combination of model checkers. For example, to start multiple model checkers in parallel and take the results of the quickest model checker, or to automatically verify different aspects of the system by using different model checkers. Besides, we are planning to extend the supported elements of SysML to make this workflow more useful for engineers and to enable the verification of the elements that they use during their day-to-day work. And last but not least, we are planning to add support for SysML v2 to have the latest version of the systems engineering standard supported. And thank you for your attention, and please let me know if you have any questions.
Thanks, Benedict. We have a question from Lucas here in the chat. I'll relay it, and then Lucas, feel free to follow up. It says, thanks for the talk. What are your plans regarding the support of other properties? Is it mandatory to have semantics in Gamma to expand the platform to other model elements like activities?
So these are two questions as far as I understood. The first one was referring to what kind of properties can be verified. So first we started at these reachability properties to find the state configuration for which the given property is true. These formal properties can be also extended so that to have not only liveness, but for example, safety properties as well. So for example, to verify that for each state in the abstract state configuration, given property is true. So this can be also extended. We just wanted to start with the property that is the easiest to demonstrate and that is the most intuitive to demonstrate for systems engineers. That would be the answer for the first question. The second one was regarding extending the supported model elements. Could you repeat it, please?
Yeah, sure. Is it mandatory to have semantics in Gamma in order to expand the platform to other model elements, like activities, for example?
The semantics of the...
Hi, Ivan, can I elaborate? Yeah,
please,
thanks.
Please.
Yeah. So I was wondering if you, for instance, you have a model checking engine already for activities, and that use a particular formal semantics, and you do not have this formalized in Gamma, but could we like plug in this strategy in a Docker container and use it in your framework without this Gamma formalism, or is mandatory to have these semantics in Gamma, for instance, for activity diagrams? Would we need to define a semantics for activity diagrams in Gamma in order to use your approach or expand your approach?
You would need to define the translation, so the transformation between the Gamma and your model checker to have it included in our workflow. And the important thing is that the transformation should be semantics preserving, because in the end, we would like to make sure that the trace that we return to the systems engineers can be actually simulated in that tool. So to verify that everything is correct.
Okay, thanks.
I had a question as well. So you explained how you're effectively hiding the formal methods application through this process of back annotation back to the the form or back to what the user receives. Can you speak to why that is a significant step, or why that's an important step to do?
What is important is that we want to make this workflow as a push button solution or as a turnkey solution for systems engineers to verify their models. So we want to hide the details from them, and we want to have an input formalism that is intuitive for them to specify what they want to verify, and then we want to hide the details of the verification. So that is the purpose of these hidden formal methods. But one of the key points of this workflow is not only hiding the details, because that has been already done following multiple solutions and multiple solutions for this problem. What one of the key points of our solution is this to leverage the cloud resources. So to enable verification of bigger models, to enable to lower the entry barrier for verification and for systems engineers to check their models.
And just a follow-up question to that, would it be fair to say that the modeler, the user of the system, wouldn't really need to learn the formal methods in order to make use of this service?
They do not need to learn formal methods. They just need to learn this formalism to define the property that they want to check. And then thanks to the returned example trace, this trace can explain how the system goes wrong, so that they do not need to learn the details of formal methods.
Great, thanks.
Hi, I have a question as well. In your later figures, you have you showed two instances of the model checking runtime. I was wondering, yes, for example, I was wondering if what you're doing is in effect parallelizing the model checking and checking in parallel different subcomponents of the system.
That is also part of the future work. So to start multiple model checkers in parallel, and to have multiple different model checkers may use different formalisms on which they evaluate the expression. For example, there are model checkers which use explicitly traversal, while the other ones are using abstractions and counterexample refinements, so that some model checkers may be more efficient to verify certain properties, while the other ones are more efficient for different aspects. And the goal of this future work is to so to say, to compete the model checkers, so that to give the same model to them to verify that, and the first one which returns the result will be taken as the result to return. So to have the quickest response, that is also one aspect.
Okay, so it's essentially, as you say, putting the model checkers to compete, but not to actually divide the task of model checking a large model into subcomponents and then checking the subcomponents independently.
That can be also a future extension, yes, to make the verification quicker and to combine and to conquer distribute and conquer the verification task. So that
yeah, okay.
I hope I said the expression correct. So to divide and conquer the verification task. Yes, that can be also explored in the future. That's also a good and interesting direction.
Okay, thanks.
Is there any future questions?
I think that might be it question-wise, but that's perfect because we're right on time here. I wanted to share my screen here. So in the last 10 minutes or so that we have here, I wanted to share where we can, oh, is it sharing yet? Can someone please confirm they can see my screen?
I can.
Going to go ahead and assume, yeah. So what I want to do with the last 10 minutes here is we can open it up to conversations about any of the topics that we've discussed today. But before we do that, I wanted to call to action where we can continue this conversation beyond today as well. So if on openmbee.org, it's kind of the homepage for this whole community. Multiple engagement opportunities here. If you go under community, I want to highlight the two main groups where a lot of the members that you spoke to today and a lot that are part of the larger community usually engage at. That would be the Google group page and the Slack channel here. So we previously mentioned that it's openmbee.slack.com, and if you click the Google group link here, you'll be prompted with more info, and you can see all the previous postings there, conversations to get a feel for it. So we look forward to seeing you there. As far as Models 2020 specifically goes, this isn't the end of the OpenMBE themed discussions either. Next, we have industry days coming up tomorrow. And if we click here and go to program, we can see some of the events for tomorrow. Sorry, this is in Pacific time, but correct that for conference time. Click. So at conference time, GMT -4, we're looking at presentations starting at 9 with introduction to OpenMBE, keynotes from industry, a number of different topics and different vendors and companies that will be sharing their experiences and developments there. So looking forward to seeing you there as well. And at this, I'll also invite any of the other co-chairs to add any notes that they may have as we wrap up here. Right, I'm going to check the chat here. Feel free to unmute and ask any questions as well.
Yeah, Ivan, maybe you can point to the non-focus page for a second to also inform the people that we are a sponsored project there.
Yes, sure. I think probably many ways to navigate there, but we go to numfocus.org, and we go to the projects, sponsored projects. You'll find, along with many libraries that you're likely familiar with. We go down, see OpenMBE here as well. So this is a recent development of OpenMBE becoming a NumFocus sponsored project. So this is going to hopefully open us up to a whole new community of collaborators through NumFocus as well.
Yeah.
So please feel free to check that out.
Not only that you can donate, but you can also apply for funds, and that might be interesting for academia as well. If you have an interesting project that would integrate with OpenMBE in some way or contribute, you can apply for funds from NumFocus.
Yep, and for anyone not familiar with NumFocus, just a little background. If you're familiar with like the Eclipse Foundation, Apache Foundation, Linux Foundation, very similar concept, with the focus that is more around open code, better science. Is their tagline there, more around the science and engineering aspects. Just going back to give a flavor of some of the projects that they are under that umbrella. a number of which we've actually talked about today. Great, and I do see some ongoing chat. I would welcome you to even after this Zoom session is over, to take the chat offline. Whether it's the Slack channel or the Google group, there's plenty more to discuss. Great. Well, I wanted to end there then, and thank everyone for participating. Thank you for the keynotes and the paper presentations, and for everyone asking questions and keeping the discussion lively. And I hope to see you at the rest of Models 2020. All right. Thanks, everyone. Bye.
Bye.